It's a real pleasure to introduce David Nesvorny. David is someone I've had the pleasure of collaborating with a couple times, and what probably accounts for 0.01% of his total publications because he's so prolific. So David got his PhD in Sao Paulo. He was just telling me today he had an office with a courtyard that opened up onto some tropical paradise. And from there he did sort of postdocs in Nice, France, and then back to Sao Paulo, and then to Boulder, Colorado. So he's really had to suffer for his places where he's had to toil away at his work. And they obviously decided to keep him on at the Southwest Research Institute in Boulder, which has been obviously very good for him and for the field. His work has been recognized, for instance, with the Urey Prize from the AAS Division of Planetary Sciences. And so David's, of course, most well known for his work in the dynamics and origin of the solar system. And I'd say his work is really kind of hard to characterize because he's someone who obviously is capable of doing almost anything. He can obviously do the dynamics of a problem, but is really to add, willing to add whatever it takes, to get the interesting and relevant scientific result. And he's been able to do that for a whole range of problems, including going into extrasolar planets, where he really did groundbreaking work in discovering non-transiting planets from their transit timing variations as well. So with no further ado, I'm pleased to let David take it over.
Thank you, Andrew. So this talk will be divided in 3 parts. I will talk about the evidence we have from the trans-Neptunian binaries about how planetesimals formed. Stephen. And the second part will be origin and evolution of the Kuiper belt. In the third part, I will discuss the planetary migration and what constraints do we have when exactly the planetary migration in the outer solar system happened. So these are some of the people, Vixingly and Ryurin, that made major contribution to this part. We all know that planet formation is one of the most fundamental problems in astrophysics. We want to know how the air formed, we want to know how the solar system planets formed, and we want to know in general how planets formed in the universe. In planet formation, one of the most problematic steps is the formation of small planets, or planetesimals, which are objects roughly between kilometer and 1,000 kilometers in size. Once an object is, say, Vesta size, it has enough gravity. So if it's given enough material, it can, at least in principle, agglomerate more and more mass and become a full-size planet. The details of that process are still complicated, but at least we know that gravity is playing the major role. On the other hand, if the first dust grains condensate in the solar nebula, they can grow to sizes about millimeters to centimeters, but they can't grow beyond that limit because of the molecular forces that hold these particles together are not strong enough, right? So therefore, it's quite mysterious how these planetesimals appeared in the first place in the solar system, and that's the subject of this first part of my talk. So there are different planetesimal formation theories, and the one which I would like to highlight here is that of a streamy instability. The streamy instability was suggested back in 2005 by Andrew Udin and Jeremy Goodman as potentially a very interesting way to form the planetesimals. Now, the streaming instability arises in protoplanetary disk because of the aerodynamic coupling between the nebula gas and the small particles there are in the gas. In short, what happens is that a small concentration of particles in a gas disk will accelerate the gas, which will create a wave, and the dust particles will migrate towards the pressure maxima, therefore amplifying that wave, and this will allow even stronger concentration of the particles. So that's one explanation. The other explanation is that the streaming instability is often compared to the peloton effect. So imagine a rider in front of the peloton. that rider has to work hard against the wind drag, right, to keep its distance. So in this situation, it often happens that the peloton captures the rider and therefore grows in size. If the peloton does it again, over and over in time, it will grow until become self-gravitating, and it collapses into a single rider. So how do we know, given that we have different models of planetesimal formation, how do we know which one is plausible and which one can be ruled out? For that, we need to look into observations. And in the solar system, one of the best places to look is the outer solar system, trans-Neptunian region, where there is a belt of small bodies known as the Kuiper belt. Now, the Kuiper belt have received lots of attention from observers, theorists trying to understand it. And one of the things that is clear is that the Kuiper belt, in fact, is a composite of two different populations of bodies. One of them is called excited or dynamically hot population. That's because it is occupying very thick disk and also has substantial eccentricities. And this population is less useful to understand planetesimal formation. This is because it has clearly been affected by some dynamical effects, and also it contains a lot of mass, so collisional evolution in that population was important. So it's not very clear what of the observational signatures they are related to planetesimal formation, and which one were modified later by just collisional and dynamical evolution. For clues about planetesimal formation, it's much better to look into a special population of bodies in the Kuiper belt that hold name called classicals. Cold classicals occupy this very narrow disk, very thin disk, which in itself is a signature that they formed in that disk and remained relatively undisturbed. Also, they represent very little mass, so there is a large chance that there were not that many collisions happening. So what we see there should be more or less primordial. So what do cold classicals tell us about planetesimal formation? So first thing is, and that's quite notable, there are binaries everywhere in the cold classicals. In fact, from observations, observers say that it's at least 30% of cold classicals that live in binaries. But in all likelihood, this number is much higher because of the tight binaries are not resolved by telescopic observation. What you can see are only the wide binaries. Now, these binaries often have, the two components in the binary have often the same brightness, which means that they are about the same size. And this is the example. So these are, equal size wide binaries that are observed in the cold classicals. That's one. Second interesting observation about these binaries is, and this is the list of all known binaries in cold classicals, that they have correlated colors. They have correlated colors because of, if you look into one binary and compare the colors of the two components, they have nearly the same color, meaning that in all likelihood they have nearly the same composition. If you look into a different binary, the color, the average color of that binary will be different from the first one, but again the two components will have the same composition. And that's an important clue about how these binaries form. Okay, so correlated colors, that's two. Now, from observations, and you have to follow these binaries for at least, say, 5 years, in the end, from the astrometry, you are able to say what's the orbital orientation of the binary orbit. So this is not the heliocentric inclination. This is actually the inclination of the mutual orbit of the two components with respect to the ecliptic. If the two components rotate in the same way that planets go around the sun, we call it prograde. If it's the opposite, it's retrograde. And this is the distribution shown in the polar plot. The prograde binaries are in this segment, retrograde are here. And from observations, people have showed that 80% of the binaries in cold classicals are prograde and 20% are retrograde. So any model that wants to explain why these binaries formed has to explain this ratio 4-to-1 preference for the retrograde orbits. That's 3. Now, how do we know if any model, and the streaming instability model in particular, fits these constraints, right? For that, we need to do the modeling, develop the theory, and make predictions. And this is exactly what we have done here with Rick Sinley, Andrew Udin, and Jake Simon, and also Will Grundy. So there are 2 stages to the formation of planetesimal. The first stage is the streaming instability itself, which acts to concentrate pebbles in self-gravitating clouds. To show this stage, we do a simulation of a small segment. Actually, it's a 3D box representing a small segment of the protoplanetary disk. It's more efficient to do it this way than simulating the whole disk, right? And what's shown here in this movie is the particle density. Of course, these simulations account for the gas, for the particles, but also for aerodynamic coupling between them, which is so important for the streaming instability. So this is just an illustration of one of the simulations we had, and as you can see, this very strong particle concentration formed in the simulation. So these are 3 snapshots from the previous simulation that Rick Sinley has done. This is initially there are these azimuthal filaments that form, then these filaments contract into self-gravitating clouds, and in the end, in this high-resolution simulation that Rick Sinley has run, we have hundreds of self-gravitating clumps.
What is the resolution there? I don't know what H is.
H is the scale height. So this whole box is about 5% of the scale height of the gas. So this is a reasonably sized box close to the midplane of the disk, but it's not covering any radial extension, significant radial extension. So unfortunately, the gravity solver in these simulations is not good enough to follow the gravitational collapse of these clouds into planetesimals, right? That's because of its Fourier-based code based on the grid, and the grid has certain resolution, and you can't just resolve anything that's smaller than that resolution. So to follow the second stage, which is the stage of the gravitational collapse, we extract some of these clouds. We assume that they are not interacting with the other clouds anymore, and we plug it into a specialized embodied code called PKD graph that disregards the effects of the gas, because at this point the particle loading or the particle concentration is so huge that the effects of gas shouldn't be important anymore. But this code is capable of accounting for mutual collisions between particles and for the growth of the objects inside. So this is what happens in these simulations. I have to say that the size of this box, if it's placed at 45 AU at the location of the co-classicals, it's hundreds of thousands of kilometers. So don't expect to see the individual objects here resolved, right? To show them, and so that you can see the physical sizes and the binaries that form in the simulation, I have to do a few tricks. I have to zoom in a little bit. I have to artificially increase the size of the symbols I'm plotting so that we can see them, right? The planetesimals that will form will be 100 kilometers across, but I increase them, I think, by a factor of 30 so that you can see them. And also I filter out all the small pebbles that are on the foreground and would be blocking the view so we don't see it. Once this is done, you can see the objects forming. Here you see the first binary. So initially there are these type binaries that form in the simulations, but many of them do not survive over the course of the integration, which might be the reason why mu69 is a contact binary. It could form through this process. But in the end of the simulation, there is a single binary surviving, and it's a wide binary in many ways resembling the one we see in the cold classicals. It represents about 30% of the mass of the initial cloud. It's aligned with the initial angular momentum vector of the cloud. And so this is very encouraging. Now,
what sets the scale of the initial? It looks like the arm breaks up into sort of a bunch of initial clumps very early on.
yes.
Do you understand that instability?
Well, I think it's just like naturally unstable on that size scale. I don't have detailed understanding of it. There are some concerns about handing over the results of the hydro simulations to the so we try to use different times of handovers to understand if this is happening in all the simulations, but I think it's intrinsically unstable to those wavelengths. But that's I have to say this is more I haven't looked in more detail to this yet. So we have done lots of these simulations, and these are our results. First, we found that the model is capable of producing nearly 100% fraction, binary fraction. This is because of all these clouds have significant rotation at the beginning. And that angular momentum has to go somewhere. And producing an equal size binary is the most economic way to distribute this angular momentum. This model applies correlated colors of binary components. This is because each of these binaries formed from a single cloud. The average composition of that cloud should tell you what the colors should be, and these two objects form from the mixture, so they should have the same colors. Then maybe later on, or a different location, another cloud will have slightly different composition, will form another binary, and therefore the two components of the new binary will have the same composition but slightly different than the one we had in the previous case. And the most fascinating result we got from this is that the model predicted binary inclination match observations. So what I'm showing here is, again, the mutual orbit inclination of the binaries, but I plot it as a cumulative number. So prograde is here, retrograde is here, perfectly retrograde 180 degrees. And the dashed line is the observations. As I was saying, there's a 4-to-1 split in favor of prograde motion. The solid line is the one predicted from the streaming instability calculation I have just shown. The dashed area is a statistical expression of a statistical error in that comparison. So there's a pretty good agreement between the two. We wished we had more binaries known in the Kuiper belt so that its comparison can be even more quantitative. But at this point, we are where we are. So this is in fact a strong argument in favor of the planetesimal formation by the streaming instability and the formation of the binaries by gravitational collapse. There has been other models like the collisional coagulation of KBOs plus a capture of two random objects in a mutual orbit, which are the ideas going back to Goldreich's paper in 2002. This model has problem to match a very high binary fraction of called classicals. It doesn't imply correlated colors of the two components because of the two objects could have formed at different locations, and therefore when they are captured, they can have any colors, right? And more importantly, even these people made predictions for the inclination distribution of the binaries, and according to them, the capture model should produce a preference for retrograde motion, a strong preference for retrograde motion, which can be ruled out by these observations. So my message to you from this first part is that there was a small peloton of particles which circles the sun until it became gravitationally unstable and collapsed into a planetesimal, right? No. It collapsed into two planetesimals. And I try to explain how these binary planetesimals help us to understand planetesimal formation. So if you have any question, this would be a good part to ask about the first part of this talk, and if not, I will continue to the origin and evolution of the Kuiper belt. Yes?
So you mentioned that you see a binary formation from your at the end of your simulation. Is it possible to have a quadruple or higher order system in your simulation?
It happens, yes. In the previous simulations that we have done in 2010, I have noticed a civil hierarchical triple systems when you had a close binary and then a distant one. The system is usually aligned in inclination, so it orbited about a single orbital plane, but it wouldn't happen too often. Only a small fraction of the simulation was giving these stable triples. It must depend on the detailed collisional accretion of the bodies, and there are some systems observed. There is one triple among Plutinos that might have just formed by this mechanism. Yes?
So I may have misheard. I thought you said that the binaries form and then they break up. They don't survive long, and then they pick up partners later on. Doesn't that then not predict the color, same color binary?
The point is that the whole cloud should have some average composition, the whole cloud. So every body that forms from that cloud should sample that average composition, right?
Okay, so
And that cloud forms just one binary. It doesn't form many big binaries. It just forms one binary, and then another cloud would have slightly different composition, and that would create another binary with slightly different composition. But again, the components of the binary would be the same. So I understand what you asked, but those exchange reactions you saw, they were happening within the same cloud. So all the bodies had the same composition in that case.
So you emphasize the ratio of prograde to retrograde, a very specific thing that comes out of your model and the very specific properties that the cold classicals have. I would curious where that comes from. I would think that that would be sort of adjustable or depend on how much random dynamical heat you have to the shear within the disk, and so it'd be something you'd measure as opposed to something you predict. Where can you explain where it comes from?
Well, so I mentioned the two stages of how the binaries form, like the streaming instability and the gravitational collapse. So what we found is that the gravitational collapse, it preserves the angular momentum. So it doesn't change whatever is set initially. So actually, in the publication we have, what we compare is the obliquity of those clouds that form in the streaming instability with the inclination distribution of binaries, because we know the obliquity defines the inclination of the binaries, and that can be compared, right? Now, as for the obliquity distribution of those clouds, we looked at the initial stages of the streaming instability, and we found initially there is no strong preference for the prograde motion. The prograde motion appears during the when the clouds become gravitationally become self-gravitating, and we interpret that as certain preference that the clouds with prograde motion, they become self-gravitating easier than the retrograde clouds. But sure, there should be a more detailed understanding of this, but we have looked into that. So it's basically that the streaming instability creates these vertical motions, allows all sorts of orientations, but then the clouds with prograde rotation, they tend to collapse better.
It's not an imprint of the original shear or something like that?
No.
Interesting.
That would be 2D, and that would just give, I think, the shear would be retrograde, in the most simplified case. Okay.
So after you form or in the process of formation of the binaries, which type of track force are the solids experimented? If they're moving fast through the solid concentration and gas, do you expect any Stokes regime to be present there, to be significant there?
If they go fast, well, they never go fast, right? I think that they remain in the Epstein regime, or
Certainly in the model. I mean, I think the main point you made is that when you get to these later phases, the drag simply stops becoming very important.
Yes.
Because, as you said.
In the early stages,
But in the early stages, it's modeled as Epstein drag,
Epstein
especially
drag,
for the
yeah.
Kuiper belts, low gas densities.
because of the velocities are really low, and given the setup, and as Andrew said, like during the late stages, the velocities are not particularly large, but I mean the particle density in these clouds is already initially, I think I look like 1,000 times bigger than the gas density, so the gas is should be, at least for these large clouds, completely negligible at that stage. Okay, so let's go to part 2, which is the origin and evolution of the Kuiper belt, which was my interest over almost 10 years now. So, thanks to surveys like the Outer Solar System Origin Survey, or also for short, we have now pretty good understanding of how the Kuiper belt looks like. The OSO survey was a 4-year project on CFHT that discovered almost 1,000 new KBOs and follow them to determine the orbits, which is important, right? You don't want just to discover and not know to which population that particular object relates. It's important that the OSOS has carefully characterized observational biases, and in addition, the OSOS team has produced what they call the survey simulator, which is a very good tool for someone doing theory because you can produce your model, your intrinsic distribution, orbital distribution. You plug it into the survey simulator, and the survey simulator kind of mimics observations, mimics the pointing direction, all sorts of leaks, sensitivity of the different frames, etc. You don't care about it. And then in the end, you get what OSOS would detect from your model, and that you can compare directly to the observation. So it's an excellent tool to be used. Now, thanks to these surveys, we know that how the Kuiper belt looks like. Before the Kuiper belt was discovered or characterized like this, I think it was expected that it would be a thin disk extending far beyond Neptune. That's because you need dynamically cold conditions for objects to form. So that was the expectation, a thin belt. But what you see here, this is the eccentricity. It's quite the opposite, right? The eccentricity rises to 0.4. It's very excited, dynamically hot belt, right? Which is a signature that something happened to this region. It was somehow affected, excited dynamically, and Neptune is the closest large planet, probably by Neptune. In addition to that, you have these columns of objects located at the same major axis. These are bodies in orbital resonances with Neptune. The most famous case is that of Pluto and Plutinos in the 3-to-2 resonance with Neptune, which is a location where the orbital period is 1.5 times larger than the orbital period of Neptune. Now, these resonances are the worst places for bodies to accrete because the gravitational perturbations from Neptune are the largest there. So therefore, bodies didn't form there, and this is often taken as an evidence, and Renu Malhotra has done pioneering work on this, as an evidence for Neptune's migration, which caused these resonances to move, sweep over that cold disk, and capture bodies inside. And I will discuss that in much more detail.
I guess since you're saying these are not cold, what's the time scale for like Neptune circularizing those orbits? I mean, I'm wondering why you're saying high eccentricity means hot.
First, Neptune wouldn't circularize the orbits because they stay for 4 billion years non-circularized. So there's no dumping effect of Neptune. It's just the terminology people use. I will show you. I will discuss this population. These are the cold classicals. So it's just terminology like dynamically hot and dynamically cold bodies. Maybe I misunderstood what you were asking. Okay. So these resonant populations are most likely a signature of Neptune's migration. But how how the details, how that in detail happen is an open question. In addition, this is the same plot but showing the orbital inclinations. These are the heliocentric orbital inclination of these bodies. And Plutinos are highlighted here, but you can see that all populations in the Kuiper belt, except for the cold classicals, which I will define in a second, have these very high inclinations, up to 30 on BM 30 degrees. And this is the observational sample. All the surveys look in the ecliptic. They detect preferentially low inclination objects. So this is even biased or compacted in inclination. The real underlying inclination distribution is even wider. So to put this in context, this is an order of magnitude more inclined than the famous Tower of Pisa. Well, I said or mentioned in the first part that there is a consensus that the Kuiper belt contains two populations. One is called classicals. They are located in the classical belt, as people say, which is the belt between 3-2 and 2-1 resonances. The cold classicals have low inclinations, which is a signature that they were not affected by Neptune's migration too much. They have not very large bodies. All the large dwarf planets are in other populations like Plutinos, the scatter disk, and elsewhere, but not in Plutinos, which is a signature that after the initial accretion, the accretion didn't proceed further. And they have these weakly bound binaries, which I discussed in the first talk. The cold classicals have very low mass, and the cold classical binaries are in fact a constraint on how much collisional evolution happened in that population. And they tell you not much. What you see there, the mass distribution of cold classicals, tells you directly about the planetesimal formation. So the implication of all this is that the cold classicals formed beyond 40 AU and survived relatively unchanged during Neptune's migration. Now the second population is that of dynamically hot objects. Well, these are the blue, green, and black symbols here. They include the hot classicals, which are in the classical belt but have higher inclinations and higher eccentricities. Plutinos in the 3-2, Tutinos, other resonant populations, and also the scatter disk, which is this disk extending to a large semi-major axis, which stays coupled. These are the bodies coupled to Neptune. So these bodies have high inclinations, which is thought to be excited by Neptune's migration. They have very large bodies, like Pluto, Eris, Makemake, and many others, Haumea, which is probably a sign that the accretion continued beyond the initial formation of small planetesimals, maybe pebble accretion. And there are no weakly or almost no weakly bound binaries, which is, as I discussed in the third part of this talk, is a sign of collisional and dynamical removal of these binaries. So the implication is that the hot populations formed below 40 AU and were implanted into their current orbits by migrating Neptune. Now, as for how exactly things happened, there were at least two different models, and which I would like to illustrate here. The one is by Johan and Reno Malhotra, published in 2005. That model postulates that the Kuiper belt formed during the planetesimal-driven migration of Neptune. Now, planetesimal-driven migration of Neptune is a process in which Neptune scatters planetesimals. It's not a planet that's large enough to scatter the planetesimal all the way from the solar system. More often it happens that it scatters them inwards to Uranus. Uranus scatters them to Saturn, and Saturn to Jupiter. And Jupiter is the large planet that can eject them from the solar system. And during this process of scattering and redistribution of planetesimals, you have to conserve the orbital energy and angular momentum. And therefore, if Neptune scatters things inwards, it must migrate outwards. And this is exactly what they assumed here. These are the migration of the outer planets in this model. This is the end result. This is the Kuiper belt model distribution they obtained back in 2005. The highlight of this model is the formation of this resonant population. As I was saying, as Neptune sweeps out, these bodies are caught in resonances, and that resembles what we see in the Kuiper belt. On the other hand, we know that this extended massive disk doesn't exist observationally, right? We know that because of the cold classicals already represent very small mass of something like 10 to minus 3 Earth masses. So whatever the profile of the outer disk was, the disk wasn't extended to tens of AU. Also, if you notice the inclination, this process doesn't excite the inclination enough. The inclination ends up below 10 degrees, maybe up to 20 degrees, but that's still not enough to explain observations. So there are some good and some not so good parts of this model. Then back in 2008, Halevison published a completely different model for the origin of the Kuiper belt. This was inspired by the NIS model instability, and this is the evolution of the planets in this case. Instead of having radial migration of Neptune to 30 AU, this model invokes a strong NIS-type instability where Neptune has encounters with Saturn, gets ejected into the outer solar disk, and then stabilizes by dynamical friction at 30 AU. So the evolution of planets is completely different. This is the end result. Again, they got kind of this resonant population by slightly different mechanism of capture than in the previous paper, but again, the inclinations are too low. Here is, Gladman has quantified this in Levison et al. Model. These are the observations for Plutinos. This is the inclination distribution according to CFEP's observations. And these are the model detections, meaning the model processed through the survey simulator. And they are largely discrepant, right? So, when I came to this, I got interested into the early evolution of the solar system. And to figure out what really happened in the solar system early on, I considered a number of constraints. Not only the Kuiper belt, but also the cometary reservoirs, the Trojans of Neptune and Jupiter, the irregular satellites, the secular structure of the outer planets, the asteroid belt, the terrestrial planets. All these constraints together to try to understand whether you can constrain what the solar system was doing early on. Now, this is one of the most plausible solutions. In this solution, Neptune migrates by planetesimal-driven migration, but then at some point, a mild instability happens. That mild instability is needed because to explain the secular architecture of the outer solar system. For example, Jupiter has small but non-negligible 5% eccentricity in its orbit. And it's very hard to understand why that should be the case, because the planetesimal-driven migration dumps the eccentricity. So if there is no instability, Jupiter ends up on exactly zero eccentricity orbit. So that's just one reason for this instability, but there are many different reasons from the structure of the asteroid belt, and if you are interested, I will talk about it more. Now, the best way to induce this instability is to have an extra ice giant between the orbits of Saturn and Uranus that becomes ejected from the solar system during the instability. Okay? It's a wild idea, but it's not necessarily wrong. So, what are the implications of this for the Kuiper belt? So, this is our Neptune eccentricity semi-major axis, and I assume that the planetary evolution is exactly like the one I showed in the last plot. Neptune will migrate and there will be instability. To simplify things, here I show just the outer disk located between Neptune and 30 AU. That this cannot continue far away, because of if it would continue, Neptune would keep migrating to larger and larger semi-major axes. So in some sense, that disk had to be truncated at 30 AU. It's not necessarily a sharp truncation, because of we know that the cold classicals are sitting here at 45 AU. Maybe it was some exponential or some other profile. And knowing that profile, I think, is an important thing to understand. But here, just for the sake of it, this is the evolution you get. So this is the state of the disk after 1 billion years of evolution. The real simulations are run over 4.5 billion years, and also I've done lots of these simulations, just tweaking different things like the planetesimal profile, the exact evolution of the planets. What you can see are the resonant populations again, but the main point comes from the inclinations. So here is the same thing, but showing the inclinations. And in this model, where Neptune migrates somewhat slowly compared to at least the wild instability of considered in Halevisson's work, you suddenly produce Putinos with very high inclinations, right? And all the belt is pretty much excited, which is encouraging. Now, on the left side, you have also observations, and on the right side, you have model, now at 4.5 billion years. This model is actually not exactly the end result of the simulation I was showing, because in this model, I assume that the profile of the disk was exponentially decaying. So I have co-classicals here as well, right? I'm trying to reproduce the whole Kuiper belt. Now, we can look at these and compare left to right. But one thing that has to be made clear is that model at this point doesn't include any observational biases, and Osso's observations do. So what I've done, I have passed the model through the Osso's bias simulator to be able to compare one-to-one with Osso's detections. And I will show you a few examples. These are not formally the best fits. These simulations are computationally expensive. I haven't done enough of them to be able to fit for the structure, but you can see at least a few, at least in rough terms, how the comparison looks like. And what I would like to highlight is the inclination. So this is the intensity distribution coming from the model. The solid line is the biased model, and the red thing are the Osso's detections. So there is a very good correspondence between this model, at least for inclinations, but for other parameters as well. Just sampling through, this is the case for the hot classicals. Again, there is a very good correspondence between observations and this modeling. But not everything works. And I was shocked that, the population I thought would be the easiest model, which is the scattered disk, gives me the biggest problems. And you can see it here, that the model detections are somewhat narrower semi-major axis than the observations. At the same time, there is a problem with perihelion distance and absolute magnitude. I'm not sure at this point if it's some deficiency of the dynamical model I have here. It may also be related to the relation between size and absolute magnitude. Maybe the albedo of large objects in the Kuiper belt increases and makes them easier detectable, which could make them detectable at larger semi-major axes, and also would increase this efficiency of detection. So maybe it's not a dynamical effect, in fact, but it might be related to the conversion between diameters, but I have to test this in more detail. But this is just to say that not everything is solved, and their Kuiper belt is full of mysteries. So this is, of course, the guy who predicted the existence of the Kuiper belt back in the 50s based on the distribution of short periodic comets. If you have any questions about this part?
So the one thing in your model that caught my eye is chucking out, an ice giant. And I'm curious if the Galilean satellites allow that.
Yes, they do.
Okay.
That's one thing I looked into. There are a few distant encounters with Jupiter, but they are not close enough to disturb the Galilean satellites too much, and that's a paper we have written in 2014. I forgot to mention that also we considered the regular satellite constraints, because if you can't have encounters that are too close. That actually is another problem of the NIS model as it was published, because in that case, if Uranus gets scattered out, then the regular satellites of Uranus get completely removed during that scattering. But it's not the case here, because of Uranus doesn't have encounters with Jupiter. So
in
your simulation that you created also some Trojans.
Yes.
Does the model match the observation?
You mean Neptune Trojans or Jupiter Trojans? Neptune Trojans. Neptune Trojans are very sensitive to, well, I have to say, like we get, it's known about Neptune Trojans that they have a high inclination spread, right? Some of them are at 30-degree inclination. So as part of the modeling, because we are able to get high inclinations everywhere, also Neptune Trojans have high inclinations in our model. So that part works. But Neptune Trojans are very sensitive to tiny details of Neptune's migration. So in some simulation, out of million bodies simulated, I get a few. In some, I get a few tens. And I'm not sure on what exactly that depends. So in some sense, Neptune Trojans are a little bit difficult to understand. But in broad strokes, as for the eccentricity, is less of a problem because of the eccentricity is limited by stability at 0.1. But the inclination, we get pretty wide inclination distribution, yes. Yes?
So if I understand right, you said you, for cases with the classical value, started with the continuous distribution and then you truncated out to the inner edge of the cold classicals.
Not really. We just continued with exponential. We started the disk at 24 AU where Neptune is sitting. That's not exactly right. Neptune could have started at 25, 23, we don't know. And then we continued exponentially the disk with, I think, one E-fold is about 2.5 AU. If you do that, there is enough mass in the disk to make Neptune migrate to 30 AU. At 30 AU, you hit the critical density, planetesimal density, that doesn't sustain that migration. So Neptune stops there. And then at 45 AU, you have enough objects to have cold classicals as they are. And then the density decays, so you don't have many detections beyond that. So it's a single profile, it's not truncated.
Okay, so is the inner edge of the cold classicals at 42 or 43 AU, is that something that's made in your simulations?
That's assumed. Yeah, that's an assumption.
Okay.
It's based on some, debris disks that show concentrations toward the inner part, towards the planet. I'm not sure. I'm just testing what the profile could be. And as an alternative to truncated disk profiles, I try to consider the exponential profile, and it works very nicely. So I thought it might be an easier solution. Now, I know I am running a little bit late, but this third part is much shorter than the previous one. In this part, I would like to answer the question, or at least constrain when planet migration happened, right? Because, and I will come to it in a second, that evidence, it turns out, comes from Jupiter Trojans. For those of you who don't know Jupiter Trojans, these are population of small bodies that follow Jupiter on its orbit. They have reflectance spectra similar to hot Kuiper belt objects, and that's usually interpreted that Jupiter Trojans formed in the same region as the hot KBOs, but then instead of being implanted into the Kuiper belt, they evolved into the inner solar system, and they were captured by Jupiter. And I will show it in more detail. The Patroclus binary, as illustrated here, is one of 20 100-kilometer larger Jupiter Trojans. It's an equal size binary, so in that it resembles the binaries in cold classicals, except that the separation of the two components is only just under 700 kilometers. While in the Kuiper belt, it's more typical to have 10,000 kilometer separation. So this is like equal size cold classical binary, but much more compact for some reason, right? And by the way, this is a target of the NASA Lucy mission. So we will learn much more about it. Now, planetary migration instability, early or late, this is an important question. Because of it has different implications for the impact history in the solar system. If the migration was late, as it was suggested, maybe 400, 700 million years after the formation of the solar system, then this could potentially explain the lunar late heavy bombardment. You may know that Imbrium Orientale have been dated to minus 3.9 billion years. And that always have been a problem. What was the source of these impactors? If, on the other hand, the migration happened early, then the asteroids and comets bombarded the terrestrial planets early, and planetary migration has nothing to do with late heavy bombardment of the moon. So it's important to establish this. Now, I mentioned the Kuiper belt. Well, from the Kuiper belt, we don't know, right? Whether the migration happened early or late, it produces the same structure. We see the Kuiper belt now. We don't know. We can't infer from the Kuiper belt when it happened. And that's the main difficulty of it, right? What I didn't show is that when you scatter that massive disk, you not only implant things into the Kuiper belt, but you also capture Jupiter Trojans. Okay? So this is an example of a body that becomes captured as Jupiter Trojan. It starts in that massive disk just above 28 AU, evolves in some way, then has lots of scattering encounters with Uranus or Neptune, then by chance ends up near 5 AU, at which point the instability happens, and that body is captured as stable Jupiter Trojan. Now, I have to say, it's extremely unlikely that this exactly happened. The probability of this is 5 times 10 to minus 7 per each body in the original abyss. But it turns out to be just the right number because of the original disk have 20 Earth masses. Then 20 Earth masses times 5 times 10 to minus 7 gives you 10 to minus 5 Earth masses, and exactly that's the mass of Trojans inferred from observations. So even if it's very unlikely, given that Jupiter Trojans have almost no mass, then this is plausible. Now, we have studied in more detail, again looking not only if we can explain Jupiter Trojan population-wise, but also if we can reproduce the eccentricity, libration amplitude, and the inclination. And all this works quite well. The dotted objects are actual Trojans. The red ones are that we produce in our simulations, and these distributions look okay. This is the inclination distribution, and again, there is a pretty good correspondence between the two. Now, coming back to this stage of scattering encounters. Now, I mentioned the Patroclus binary, right? And now I look at it and thought like, well, does the Patroclus binary survive during these encounters? Imagine it was a binary at the beginning. It had to go through this complicated evolution. It came many times close to Uranus and Neptune. Would it survive? And in fact, there is a clear condition whether it would survive or not, right? If the planetocentric helisphere of the binary becomes smaller than the separation of the binary, it wouldn't survive. And then depends on how deep the encounters are, okay? So I decided to, well, that's an interesting constraint. Let's see if this implantation model is plausible. Patroclus binary better survives, right? Otherwise, it can be ruled out. So I looked into this in more detail. I followed that trajectory and many other trajectories. I assume many different binaries with different separation, ranging from 100 kilometers, which would be a contact binary, to something like the cold classical Kuiper binary at 10,000 kilometer separation. And this shows the surviving binary fraction. So if you consider the cold classical binaries, the wide binaries, the surviving fraction is negligible. You don't, if the Patroclus binary would be separated, that would be a problem. But in fact, the Patroclus binary separation is about 700 kilometers, and for that, the survival probability is about 70%, and that's fine, because Patroclus binary is just one of 20 objects of Jupiter Trojans that is a binary. All the other ones are not binaries, right? So that's plausible, it survives. But then I thought, well, if we are talking about the survival of the Patroclus binary, it's not only dynamical survival, it's also the collisional survival. And that was something suggested for the Kuiper belt by Petit and Moses, but not in this context. But the effect is the same. If you have a Patroclus binary, the orbital speed of that binary is about 10 meters per second only. 10 meters per second, not kilometers, meters per second. So if there is a small impact that just transfers linear momentum to one of the components, and the delta V is of the order of 10 meters per second, then the binaries is dissolved, right? Flies away, and it wouldn't exist. So I thought, well, this could be a cool way to constrain when the planetary migration happened, because if the migration was delayed, the 20 Earth mass disk existed for 500 million years, say, and then it would have evolved collisionally, thus destroying all these wide binaries that would form in it, right? So I will look into this as a constraint, how long that massive disk lived, and by extension, when planetary migration happened and eliminated this. And the results were interesting. This shows the collisional survival, again as a function of the separation of the binary. And for different disk ages, 100 million years, 200 million years, up to 600 million years. So, for example, if you look at the case that would be compatible with the LHB, the disk would live for 500 million years. The survival probability is 10 to minus 5. And this can be ruled out because of then it would be completely unlikely that the Patroclus binary exists among 20 largest Jupiter Trojans. On the other hand, ages of the disk 100 million years or shorter are completely plausible. For example, at 100 million years, the survival probability is 10%. So if, say, the original fraction of the binaries was 50%, multiplied by 0.1, you get 5%, and that's 1 in 20, which is exactly. So this constrains the fact that the disk was dispersed by Neptune within the first 100 million years, and my personal opinion is that the disk, the Neptune, start migrating immediately after the dispersal of the gas nebula. And this is the end of the talk. I'm sorry for being 10 minutes late, and these are my conclusions. And if you have any questions, I will be happy to answer them. Thank you.
Any more questions on section 3 or the others?
Would a Patroclus binary be detectable at 38 years? I guess
It would not.
Yeah. So you don't have any observational evidence that there are no Patroclus binaries?
They should be, in fact.
Should be detectable?
No, they should not be detected, but they should be these binaries. I think once the detection, is there should be there, because Patroclus binary, it was detected only because of it survived all this scattering and collision evolution, and it came back closer to us so that we can resolve it. The ones that were scattered into the Kuiper belt, they would also survive, and I looked into that in detail. They would survive, but they are not detectable at this time. So
it's very close, though. I mean, it's about 30 million arc seconds or something. So the technology is very close.
It's getting there, yes. So in a sense, prediction of this model would be the deeper or the more resolution we have, the more binaries we find. And I think that's the case, right? Because of the binary fraction, even like there are many more binaries at closer separations than very large separations. So.
Yeah, David, this last part, it seems to me it rests on a lot of tenuous assumptions.
Yes.
So, for example, it could well be that the migration happened late, but for reasons very different than what you're assuming. There's one idea that's been around in the literature that Uranus and Neptune formed late. And, the migration doesn't happen until Uranus and Neptune grow up. So,
yes, but still.
That rules that out. I think
but so one big assumption there is the Jupiter Trojans were implanted by the mechanism I described. That's one big assumption, because of there are other models for Jupiter Trojans. The recent one comes from Johansen group. They say that Jupiter formed at 25 AU, now even at 30 AU, and migrated inwards during the gas phase, therefore capturing planetesimals as Jupiter Trojans, right? So they have this completely different model. They capture a few Earth masses of Jupiter Trojans, so they have to eliminate everything. They initially said maybe there are big planetesimals or big embryos captured together with Trojans, and then those embryos just erode the population over time. So there are different models, but this is a big assumption, right? But then, as for the assumption, what was the reason that Neptune started migrating? I think there's no assumption built in there, because independently when Uranus and Neptune formed, the planetesimals formed in the gas disk, right? And that presumably tens of Earth mass disk should have existed to drive Neptune's migration. When Neptune formed, right, we don't know, but it's not a constraint what triggered the migration. It's about the constraint that that disk, massive disk, couldn't have lived for more than 100 million years. If it would, the particles binary wouldn't be there.
I don't agree with that.
Okay.
You're missing a connection there.
Okay.
So I was wondering, you said that the Petricus binary was among the 20 largest objects and
Yes.
the only binary of those, but is it known or would it be expected that any of the smaller Trojans would be binaries?
There's one. So I think among the largest objects, there's no resolved binary. Hector, which is the largest Jupiter Trojan, is a contact binary, right? And it has a small satellite also for some reason. And then I think there are two other Jupiter Trojans, smaller, more like 50 kilometers in size, that are also equal-sized binary, tight equal-sized binaries. So, and then, you know, many remain unresolved, unlooked at. And so at smaller sizes, it's not quite clear what the binary fraction should be.
Yeah, obviously I'm getting at whether this can be used to test the idea that all planetesimals formed as binaries.
Sure.
Obviously many of them would be disrupted,
Yes.
but some would survive. So, okay, if there's no other questions, let's thank David again.
Thank you.